Assalamualaikum warahmatullahi wabarakatuh, and hello to all. So basically, I'm going to continue to give the video lecture on chapter 4, but this time around we're going to look into design of Cstr in isothermal condition. Okay, again, have you got the answer what is isothermal all about? So it is important for you to identify and to know what is isothermal reactor. The design of Cstr, you have known already that in terms of single reactor, we have basically a formula where you have developed this kind of formula. V equals to Fa naught minus Fa over negative Ra, and you already simplified it, become Fa naught x divided by negative Ra. How do you get that? Then you have to revisit chapter 3, stoichiometry. And for a constant volume system, you remember what condition that can give you constant volume? Which is there is no expansion, okay? Which is in liquid phase, for example. So V equals to V naught multiplied with Ca naught minus Ca divided by negative Ra, where Fa naught equals to Ca naught, the concentration of species A, multiply with the volumetric flow rate. And then if you go to single reactor as well, in terms of the space-time, tau is equals to V over V naught, which is the volume of Cstr, or volume of any kind of reactor, PFR for example, divided by the volumetric flow rate of it. And in this particular case, it is equivalent to Ca naught minus Ca over negative Ra. This is after you have rearranged this particular equation, and you get the information of tau, which is the space-time. So now we like to incorporate the negative Ra equals to Kca, which is with relation to the first order of reaction, into tau. And finally, you can get tau equals to Ca naught minus Ca divided by Kca. So you just replace this term, and you put Kca here. And when you rearrange the equation, you will get Ca equals to Ca naught divided by 1 plus tau k. Okay, so as for Ca equals to Ca naught times 1 minus x, when you rearrange the equation, you will get tau k divided by 1 plus tau k. So what is so significant about tau k? This is not tau k at the kedai, okay? It's different. So that particular tau k, it is important because it gives a definition of Dampf-Kohler number. I'm not sure whether I'm spelling it, I say it correctly or not, but it's Dampf-Kohler number, dA. So dA is basically a measure of whether it gives a quick estimate on the degree of conversion in Cstr, which is given in terms of equals to negative Ra naught V divided by Fa naught. Okay, so you know that negative Ra naught, and then you know also V, the volume of Cstr, divided by the Fa naught. So from here, you can estimate what is the degree of conversion in Cstr. If let's say that you have, you already have an existing Cstr, you know what is the flow rate, the molar flow rate coming in, and you know what is the rate of reaction. So you compute everything, then you got your Dampf-Kohler number. If let's say that Dampf-Kohler number gives you very less amount, which is less than 0.1, then you can expect that your conversion is going to be very, very low. But if let's say you're going to put dA more than 10, then you're going to have a higher conversion. So in this particular case, you will have first order irreversible reaction, the Dampf-Kohler number dA equals to tau k, but for second order irreversible reaction, dA equals to dkCA naught. How do you do this? So why not you try yourself to derive the equation? So, in terms of design of Cstr, you already learned about designing Cstr, a single Cstr reactor. But how about you design the Cstr in series, for example? So for Cstr in series, we assume first of all is, let's say this is a first order reaction with no volume change. So what happens is that there is an initial concentration coming into your reactor. Then basically there is a certain rate of reaction, RA1, negative RA1, with a specific volume of V1. And then the exit concentration of your Cstr become the inlet concentration for the second Cstr. But during that particular time, you already achieve some conversion, X1. And then when it goes to the second Cstr, again there is another rate of reaction, negative RA2, with another volume V2. And now the exit concentration is Ca2 with another conversion achieved, which is X2. So in order for us to design this Cstr in series, initially what we have to do is basically we measure if you remember the equation again, Ca1 equals to Ca naught divided by 1 plus tau 1 K1. Okay, so this is the exit concentration of reactor 1. This is the inlet concentration of reactor 1 divided by 1 plus tau 1 K1. Tau, if you can remember, is basically the volumetric flow rate. Sorry, the volume divided by the volumetric flow rate. Okay, and multiply with the rate constant. And concentration of A at reactor to exit is now Ca2. It is the exit concentration. But the Ca1, which becomes the exit concentration for reactor 1, now it becomes the inlet concentration for reactor 2. And you also divided it by 1 plus tau 2 K2. And if you relate back to the whole system, okay, for which that the initial concentration is actually Ca naught. And therefore, you have to multiply 1 plus tau 2 K2 multiply with 1 plus tau 1 K1 to represent the whole, in order for you to calculate Ca2 as well. So this is equivalent terms. Therefore, if the volume of both reactors are the same, and the volumetric flow rate entering the reactors are the same, therefore, tau 1 equals to tau 2. So if let's say V1 equals to V2, and the volumetric flow rate is the same, therefore, you can straight assume tau 1 equals to tau 2. If the temperature is isothermal for both reactors and the same operating temperature, therefore, you can assume that the rate constant is the same. So which means that if let's say the V1 is 100 degrees Celsius, V2 is also 100 degrees Celsius, so you can assume that the rate constant is the same. Therefore, you can simplify it further. If let's say we rearrange that this particular Cstr with the same volume, the same reaction temperature, the same and then the same volumetric flow rate, therefore what we can do, we can simplify it further. Can equals to Ca naught divided by 1 plus tau k to the power of n. And then when we put in terms of conversion, it becomes x equals to 1 minus 1 over 1 plus tau k to the power of n. So how do you get this particular conversion? So you have to come across the mind in terms of Ca naught and Ca, and then you put this particular term in terms of the conversion. Okay. If we refer, for example, like we want to look at the pattern, if let's say we design this particular Cstr in series, what happens if let's say the tau k, this is related to the first order of reaction, okay, as stated here. How about if let's say we vary the tau k, which means that, okay, now we assume that k is constant because it is reacting at the same temperature. So k here is constant, k here is constant, k here is constant. The volume of the same reactor is the same. But now what happened is that we only change in terms of the V naught, which means volumetric flow rate, we change it. So that's why if let's say V over V naught here become tau k equals to 1, and then tau k equals to 0.5, tau k is 0.1. So you can see the pattern here in terms of the graph here. The higher the value of tau k for first order reaction, then the faster it reaches the conversion. For example, here you can see that we only required until up to 8 tanks in order for us to achieve the conversion for 1. But if let's say tau k equals to 0.5, even 10 tanks is still not enough. Maybe we need maybe 12 or 13. Okay. And if let's say the reaction happen very slow, for example, like you are putting at very in which, for example, like V is fixed, but you're operating at very fast flow rate. It gives a very low tau k, which is equals to 0.1. Okay, so because there is no enough time of the reaction to happen in one single reactor, so it moves to another reactor, and then still because the volumetry is so fast, again it moves to another reactor. Therefore, if you can see from here, I think maybe it needs up to 30 or 40 Cstr tank with equivalent size in order for it to get higher conversion, maybe up to 1. Okay, so the Dam-Kohler number give you a very good estimation in order for you to design the Cstr in series. If let's say we design Cstr in parallel, for example, we have negative Ra1, V1, negative Ra2, V2, then we assume equal reactor size and similar operating temperature and feed rate. So what happens is that the conversion will still be the same. Even the rate of reaction will still be the same. The volume of individual reactor is basically is equals to the total volume divided by number of tank. Similarly, you are breaking down the flow rate. Fa naught I equals to Fa naught N. So the balance on I from individual reactor volume. So when you rearrange the equation and sort everything, you can cancel out N and N. So there is no point actually for you to arrange the Cstr in parallel, because it will just be equivalent to the single volume. Which indicates here is that no matter how much Cstr that you arrange in parallel, you will achieve the same conversion. So there is no increase of conversion when you put it in parallel. This is what it's trying to say by when you try to arrange Cstr in parallel. So there is another example that I would like you to go for production of ethylene glycol in a Cstr. You can spend your time to read this, and then we can do some example in the class afterwards. You can show me how that you are doing this kind of example based on the formula and the equation that I give earlier. I think that's all for now. Thank you very much. Bye-bye.